All right, today we are going to tackle a word that sounds, let's be honest, a little intimidating. Stoichiometry. But I promise you, by the end of this, you're going to see that it's really just a recipe book for chemists. So let's open it up and see what's cooking. So here's our game plan. We'll start with what stoichiometry even is, then figure out how chemists count tiny little atoms. After that, we'll learn to read the chemical recipe, get into the math behind it all, and talk about what happens when you run out of an ingredient. And finally, we'll put it all together and solve a problem. So, first things first. At its heart, stoichiometry is all about answering one simple question. A question any good cook or chemist absolutely has to ask before they even get started. And that big question is, how much stuff do I actually need to mix together? Right? I mean, if you're baking a cake, you can't just guess how much flour and sugar to use. Well, in chemistry, it's the exact same idea. And stoichiometry is the tool that gives us the precise measurements. Okay, so here's the official definition. It's all about the quantitative relationships, which is just a fancy way of saying the amounts between your reactants and your products. And to keep our cooking analogy going, just think of reactants as your ingredients and the products as the delicious final dish you're making. It's really as simple as that. Now that we know what we're trying to do, let's figure out how we measure everything. Before we can start mixing our chemical ingredients, we need a standard way to count them. And in chemistry, we have a pretty special unit just for this job. And that unit is the mole. Now, it might sound like a fuzzy little animal, but in chemistry, a mole is just a word for a specific number. It's exactly like how we use the word dozen to mean 12. When a chemist says they have 1 mole of something, they're just counting out a standard amount. You can think of it as the chemist's dozen. But here's where things get kind of mind-blowing. 1 mole isn't just 12. It's this number. An absolutely enormous number. 6.022 times 10 to the 23rd power. It's called Avogadro's number. And why is it so gigantic? Well, it's because atoms are so incredibly tiny that we need to group them into these massive quantities just to work with them. Okay, so we know how to measure our ingredients using the mole. Now we need the actual recipe card that tells us the exact proportions to use. In chemistry, that recipe is what we call the balanced chemical equation. And this recipe has one golden rule, a non-negotiable rule. It must be balanced. Why? Because of a fundamental law of the universe, the conservation of matter. You can't just magically create atoms out of thin air, and you can't make them disappear. You can only rearrange them. So whatever you start with, you absolutely have to end with. Let's see this in action with a super common recipe, making water. The recipe says 2H2O plus O2 gives us 2H2O. Now let's do a quick head count. On the left side are ingredients. We have 4 hydrogen atoms and 2 oxygen atoms. And on the right side, in our final dish, what do you know? 4 hydrogen and 2 oxygen atoms. It's a perfect match. The books are balanced. All right, now for the part where the rubber meets the road. We've got our measuring unit, the mole, and we've got our recipe, the balanced equation. So let's look at the actual techniques chemists use to crunch the numbers. Now, there are a few different types of calculations you can do, but they all basically involve converting between moles and mass in grams. But honestly, the most common one, the one that's the real workhorse in any lab, is this last one, mass to mass. And here's the secret sauce for how to do it. It's a simple 3-step dance. If you know the mass of an ingredient, first you convert it into moles. Then you use your recipe, the balanced equation, to see how many moles of the final product you can make. And finally, you convert that number back into a mass. It's a foolproof roadmap that works every time. But, in the real world, things aren't always so perfect. What happens when you're halfway through baking cookies and you realize you're out of chocolate chips? Well, chemistry has a name for that exact situation. This brings us to what we call limiting and excess reagents. The limiting reagent is simply the ingredient that you run out of first. It literally limits how much of your final product you can possibly make. The excess reagent is the stuff you have plenty of. You'll have leftovers of it when the reaction is all done. And just like in the kitchen, sometimes things go a little wrong. Maybe you spill something or the reaction doesn't go to completion. That's where percent yield comes in. It's a super simple comparison of what you actually made in the lab versus what your recipe, the math, said you should have made. It's basically a report card for how well your reaction went. All right, we have covered all the theory, the rules, and the real-world curveballs. I think it's time we put all of this awesome knowledge together and actually walk through a problem from start to finish. So, here is our challenge. We're going to make some water. The question is, if we start with exactly 4 grams of hydrogen gas, how many grams of water can we possibly make? And we've got our trusty balanced recipe right there to guide us. Now, we don't have to guess how to solve this. We have that reliable 3-step mass-to-mass plan we just talked about. We're going to follow these steps exactly, one by one. First up, step 1. Let's convert our starting mass into moles. We have 4 grams of hydrogen, and its molar mass is about 2 grams for every mole. So we just do 4 divided by 2, and that gives us 2 moles of hydrogen. See? Easy enough? Now, for step 2, we have to look at our recipe. The balanced equation shows us that for every 2 moles of H2 we put in, we get 2 moles of H2O out. So it's a 2-to-2 ratio, which of course simplifies down to 1-to-1. That means if we start with 2 moles of hydrogen, we're going to get 2 moles of water. And finally, for our grand finale, step 3. We need to convert our 2 moles of water back into a mass we can actually weigh. The molar mass of water is about 18 grams per mole. So we take our 2 moles, multiply by 18, and that gives us our final answer. And there it is, 36 grams of water, all from just 4 grams of hydrogen. And just like that, you have successfully used a chemical recipe to figure out exactly how much you can make. You just did stoichiometry. So you see, stoichiometry isn't some scary, complicated monster. It's just a logical, incredibly powerful tool. It's like having the recipe book for the entire molecular world. Now that you know how to read it, the only real question left is, what are you going to calculate next?